Starting webinar in 5, 4, 3, 2.
Good morning, everybody. Before we start, and as people start rolling in, I just want to let everyone know that we will be recording this webinar so that we can post it on our website at a later time for people who can't make it today. So we're going to wait just a minute for people to come in, and we can see them rolling in on the participants panel. And once we hit critical mass, we'll launch the webinar for real. And we'll start in just a minute. Okay, it's 10 o'clock. Why don't we get started? Good morning. Welcome to today's Future Supply Actions Funding Program webinar. Today's webinar is on the Thousand Oaks Groundwater Utilization Study. My name is Warren Tights. I'm a team manager in Metropolitan's Water Resources Management Group, and I'm also the program manager for the Future Supply Actions Funding Program. We call it the FSA program, and I'll be your moderator for today. We're going to get started shortly, but let me go over a few housekeeping items first. As I mentioned earlier, we're recording today's webinar, so your microphones are muted. Any dogs that you hear barking are mine, and I apologize for those in advance. The recording, slide deck, and other materials will be posted on our website in the near future. We hope to have some time for Q&A at the end of the webinar, so please type your questions in the Q&A box. And finally, we do plan on ending on time. We value your time, so we're due to end at 10:45, and we plan to hit that goal. Next slide, please. So we'll go through some welcome introductions, then hit the presentation, and then Q&A. Next slide. Before we start, I want to give you a brief overview of Metropolitan and the Future Supply Actions Funding Program. So as most of you know, Metropolitan is the primary wholesale water provider in Southern California. We supply water, our wholesale water supplies to 26 member agencies that serve 19 million people and a $1 trillion economy. Metropolitan imports water supply from the Colorado River and from Northern California through the State Water Project. Next slide. So over the past 30 years, we've invested billions of dollars to diversify our resource portfolio. That includes investments in storage, transfers, conservation, and local supplies. And innovation in local supplies is going to be fundamental to our success as a region as we continue to advance our One Water future, our One Water approach. And this is where our Future FSA program fits in. Next slide, please. The FSA program was established in our 2010 Integrated Resources Plan with the goal of driving innovation in local resources. Through our program, we collaborate with our member agencies to fund studies that pilot new approaches, pilot new technologies that create new supply development opportunities by addressing barriers to supply development. That could include technical barriers, institutional barriers, and regulatory barriers. Benefiting the region is the core principle of the FSA program, and thus the purpose of this webinar. We want to share the results of these studies with as many people as possible. Finally, water agencies, the water industry is risk adverse. It's through these studies that we de-risk technologies so that we can apply them to our operations. Next slide. So our current FSA program includes 14 studies with our member agency partners, and they cover all 4 of the resources under the FSA program: groundwater, stormwater, recycling, reuse, and desalination. But we've also funded 7 studies with the Water Research Foundation related to reuse and agricultural reuse. These studies not going to help us with this current drought that we're in right now, but they will help us with future droughts, the next drought, and the droughts to come. So next slide. All right, so the focus of today's webinar is the Thousand Oaks Groundwater Utilization Study. And this study evaluates the use of closed circuit reverse osmosis, or CCRO, as applied to brackish groundwater desalination. Our member agency partner for this study is Calleguas Municipal Water District. And our presenters today include Ida Feruzin. She's an associate engineer with the City of Thousand Oaks Public Works Department. And Steve Diamond, he's a senior project manager and water treatment expert with Kennedy Jenks. And at this point, I'll turn it over to Ida to introduce the study and launch the presentation. Ida, take it away.
Good morning, everyone. Thank you so much for joining us today. First of all, on behalf of the city, I would like to express our deep appreciation to Metro Water District and Calleguas for supporting our project. Currently, the city's primary water supply is imported from Northern California through the State Water Project. As you know, the availability of the imported water is subject to long-term hydrologic pattern in the delta and can be substantially constrained during sustained drought conditions. As a result of these issues and increasing cost of imported water, the city is looking into developing local sources of water. Next, please. In 2016, city hired CDM Smith to prepare a study to evaluate the feasibility of developing local water supplies. The study concluded that Conejo Valley Groundwater Basin is a viable source of water for the city, and a near-term recommendation was to put the existing well located at the Los Robles Golf Course back into service and treat the groundwater. To take this study to a higher level in 2018, city hired Kennedy Jenks to evaluate the feasibility of treating the groundwater at the golf course well to meet the groundwater quality standards for both irrigation and potable water. This study looked at 3 critical issues, including sustainable flow from the well, treatability of groundwater, and the brine disposal feasibility. And the recommended treatment technologies included conventional reverse osmosis and closed circuit reverse osmosis as primary treatments with green sand media filter treatment for iron manganese removal. In March 2019, a 6-month pilot project was implemented to better optimize the treatment process and also to refine the design criteria, which is our presentation today. Then in August 2020, we started to pump the well at a flow rate of 770 GPM over an extended period of time to confirm the sustainable yield of the well. The pumping was terminated in March 2021, and currently Kennedy Jenks, with the help of Hopkins Groundwater Consultants, is monitoring the recovery of the basin to determine the sustainable yield of the well. We are also wrapping up the environmental document for the project, and we'll be taking the MND to the city's council for adoption in September 2021. Next, please. And here is a layout of the proposed project. The blue circle is the existing well at the golf course. The purple line is the proposed raw water line, conveying the flow from the existing well to the proposed treatment facility, which is shown in light green. And the dark blue line is the proposed product water line, conveying the treated water from the proposed treatment facility to the city's water distribution system. Next, please. And as I mentioned, in 2019, we conducted a 6-month pilot project. The goal of the pilot project was to refine the raw water quality and design criteria for the key unit processes, including iron manganese pretreatment, reverse osmosis, and closed circuit reverse osmosis. Another goal was to optimize performance of treatment trains and also to optimize operation and maintenance requirements. And last but not the least, to provide the city with the operational experience. And now I'm going to hand this off to Steve to go over the technical aspects of the project. Steve, it's all yours. Thank you very much.
Sounds good. Thank you, Ida. So the first few slides we'll go over are on the equipment and the methodology, and then the last few slides are on the findings and the results. So as Ida just mentioned, this project is treating a brackish groundwater in the Conejo Valley groundwater basin for both golf course irrigation and potable water uses. As a result of the treatment goals for both uses, desalination is required. And so conventional RO and CCRO, or closed circuit RO, were identified in the feasibility study and the draft PDR as the primary treatment alternatives, which both utilize RO membranes and were identified for comparison as part of this pilot test. A key component for these processes is pre-treatment, and the historical groundwater quality indicated elevated iron concentrations. So this pilot testing looked further at the pre-treatment requirements with respect to iron. The alternatives were essentially iron removal versus no iron removal. For iron removal, we tested oxidation and filtration using chlorine, green sand filtration, and sodium bisulfate for dechlorination prior to the reverse osmosis and closed circuit reverse osmosis systems. Next slide, please. So the primary treatment alternatives included conventional reverse osmosis, which is a pressure-driven process where the pressure is boosted to exceed the osmotic pressure of the water, with a water quality TDS of approximately 1,500 milligrams per liter, and producing a continuous stream and permeate stream and concentrate stream. The RO process included multiple concentrating stages to increase the recovery of the system, typically with 6 or 7 elements per pressure vessel. Additional requirements identified included iron pretreatment, as I discussed earlier, and cartridge filtration and chemical conditioning with antiscalant and sulfuric acid for pH adjustment. Next slide, please. So the primary treatment alternatives also included closed circuit reverse osmosis, which is a semi-batch process where the concentrate normally recirculates to the feed side of the membranes. The CCRO system can use the same RO membranes as with conventional RO. It is typically configured in a single stage array with 4 to 5 elements per pressure vessel. Typically, the CCR system, RO system flushes the concentrate through a dump valve when the target recovery is met. Next slide, please. So this is the process flow diagram for the overall pilot system. As discussed, the system included 2 primary treatment trains operating in parallel to compare conventional RO versus CCRO. An existing well that Ida mentioned, which would be used for the full-scale project, was equipped with a submersible pump and plumbed to the pilot system. The pilot program was broken out into 4 separate tests. Test 1 was a baseline scenario for the conventional RO only that did not include iron pretreatment. Test 2 tested the same conventional RO with the addition of iron pretreatment. And tests 3 and 4 included operating CCRO with iron pretreatment connected in parallel to conventional RO. Test 3 was intended to be a comparison of the two at the same basic operating conditions, with test 4 intended to be an optimization of the process, of each process. Next slide, please. So this is a schematic of the pilot system layout, which was located in a remote parking lot at the Los Robles golf course. The raw water feed from the well comes into the picture from the left, feeding the conventional RO train on the top and the CCRO train on the bottom of the page. The trailers or the containers for each system included their own separate iron pretreatment, which were based on the same design and intended to operate on the same operating parameters. The red outline around the treatment systems is a fence, which was provided to contain the pilot system as part of the overall safety and security measures. Next slide, please. As noted, the, the pilot test was broken into 4 separate tests, including a startup mobilization period and a shutdown demobilization period. Each of the 4 tests were scheduled for 6 weeks of operation, but the actual durations were extended for most of the tests as a result of typical pilot testing issues, such as mechanical issues with the pumps or instrumentation failures, or to conduct unscheduled cleanings or CIPs. Next slide, please. So the pilot test learning summary. So starting with test number 1, test number 1 was on the conventional RO, only without iron pretreatment. And the RO system was tested at a recovery of 79% with antiscalant and sulfuric acid for pretreatment conditioning. The testing parameters for the first test were based on desktop evaluations performed during previous work that I was discussing earlier, and historical raw water quality from the LRGC well. One of the benchmarks for each test was a projected CIP frequency of 3 to 6 months based on the evaluation of normalized data during the test. And this test did not achieve that goal. One of the key observations during this first test was on the raw water quality, and that the silica was the limiting scalant for conventional RO. Silica concentration during testing was significantly higher than the previous historical data. Test number 2 was also conducted on conventional RO, but with iron pretreatment added, and it was also tested at a 79% recovery. The pre-pH adjustment with sulfuric acid was no longer added based on the results of the first test. And the CIP frequency goal was also not achieved. And it was determined that the recovery of 79% was too high for this raw water quality. So in test number 3, it included both RO and CCRO. Both systems were operated at lower recovery of 76%. With an objective of establishing the minimum successful conditions for each system. The CIP frequency goal for conventional RO was achieved, confirming the recovery of 76% and no pre-pH adjustment. The third test for CCRO experienced issues with operations of the iron and pretreatment system that forced multiple CIPs during the testing period. But it afforded us the opportunity to identify and resolve those issues for the 4th test to make a better comparison. Test number 4 compared RO versus CCRO. Both systems were started at 76% recovery based on the benchmark achieved by the conventional RO in the previous tests. From a scaling fouling perspective, the conventional RO performed as before at these conditions. But the membranes were damaged as a result of overfeeding chlorine in the iron pretreatment system, which ended that test early. For the CCRO, the acid was added for pre-pH adjustment, and the recovery started at 76% and was increased to 82%. There was limited scaling or fouling identified during this test for the CCRO, and the CIP frequency goal was achieved. Next slide, please. Test number 1 results summary. Test number 1 was performed at a recovery of 79% on conventional RO, and the results indicated that this was too high for this configuration. The membranes were autopsied at the end of the test, which indicated both iron fouling in the lead elements and silica scaling in the lag elements. With silica scaling as a limiting scalant, pre-pH adjustment with sulfuric acid was proving to be counterproductive and was discontinued in subsequent tests for conventional RO. Next slide, please. So test number 2 summary, results summary. Test number 2 was also performed at a recovery of 79% on conventional RO with the addition of iron pretreatment. And though the results did not show iron fouling in the lead element, they confirmed that the recovery needed to be lowered as a result of silica scaling. In fact, the buildup of silica on the membranes during this and the previous test appeared to be the cause of damage to the lag elements. So when CIP was performed, it did not restore performance. The membranes were placed in the conventional RO system for subsequent tests. Next slide, please. Test number 3 was performed at the lower recovery of 76% on conventional RO with iron pretreatment. The results confirm that this is as a successful scenario by meeting the projected CIP frequency goal. Next slide, please. Test number 3, CCR results summary. So test number 3 for CCRO experienced a number of starts and stops and included 2 CIPs. This was as a result of issues with the iron pretreatment system and iron fouling on the membranes. This further confirmed the need for iron pretreatment. Of note, though, after the second CIP, the iron pretreatment system was performing better, and the rate of increase of normalized DP was significantly lower than earlier during this test. Next slide, please. Test number 4 results summary. So test number 4 for conventional RO was intended to be operated at similar test conditions to test number 3. The performance started off similar as before, but approximately 3.5 weeks into the test, it appears that the membranes were damaged as a result of overfeeding chlorine in the iron pretreatment system. The sensitivities to over and underfeeding chlorine and also say over and underfeeding sodium bisulfite were understood going into the test, but the performance demonstrated at least one of these in this case. Instrumentation and controls on a pilot system can be limited, but including alarms and automatic shutdowns based on critical set points, such as ORP, was a recommendation for full scale. Next slide, please. Test number 4 results summary for CCRO. So for CCRO, acid was added for pre-pH adjustment. The recovery was increased to 82%, starting from 76%. As I know before, there was limited scaling of fouling identified during the test, and the CIP frequency goal was achieved. With each of these, as were the treated water quality goals. The recovery of 82% recovery was capped as a result of time allowed for the test, but the results indicated that higher recoveries could be feasible. Next slide, please. Overall pilot test findings. The pilot test findings include they provided a greater understanding of the range of concentrations to be expected from the LRGC well, including identifying silica as the limiting scalant. The previous studies suggested that calcium carbonate was the limiting scalant, so this was a significant finding. The results confirmed the need for iron pretreatment to meet the operational goals, and they demonstrated the disadvantage for pre-pH adjustment on conventional RO and the need for it on CCRO to optimize recovery. They demonstrated the sensitivities to RO from iron pretreatment, bioxidation, filtration, and helped to identify additional instrumentation and control measures to mitigate these for full scale. And they allowed us to refine the recoveries for both conventional RO and CCRO and demonstrate the limits and potential for each. And they also allowed us to refine the bypass blending ratios required for each of the irrigation and potable water uses. Next slide, please. So the regional applicability, this includes, for example, the CVGB is high in TDS, as are some other regional basins, resulting in the need for desalination, which would likely be RO, or could likely be RO. By comparing alternative RO technologies and optimizing recoveries for each alternative, there can be opportunities to further maximize the value of groundwater supplies, as demonstrated in the pilot study. The pilot study results indicated that CCRO is a feasible alternative for primary RO treatment of a brackish groundwater source, with opportunities to perform at higher recoveries than conventional RO. And the pilot study addressed iron pretreatment to optimize RO performance and demonstrated some of the sensitivities and mitigation measures to RO membranes of the chemical feeds associated with oxidation and filtration. Next slide, please. So that's it. Open it up to questions. Or give it back to Warren.
Well, okay, I'll moderate the Q&A session. That was a terrific presentation. Thank you, Ida and Steve. This is a terrific project, and you know, I can see this benefiting any of the water agencies in our service area looking to maximize or expand the use of the brackish groundwater for their customers. We do have a question in the chat box, and I think, Steve, this is addressed to you. Let me read it for you. And this is from Steve Deschamps. Did you consider sequestering the iron and manganese with pretreatment chemicals instead of green sand removal?
It's a good question. We did consider that as an alternative, sequestering the iron. I think one of the reasons why we didn't is we had some time limitations in the overall piloting program schedule. So we focused on really looking at the advantages and disadvantages of removing the iron versus not removing the iron. So that's why we focused on oxidation filtration versus not removing it at all. Okay.
Hopefully that answered your question. We've got another question from Richard Breckenridge, and this could go to either Ida or Steve. And this is a question I had as well. So what is the end location for the brine? So the brine disposal is the Achilles heel for brackish groundwater. Where does this brine go?
Actually, it goes to the city's wastewater collection system. We had a sewer manhole just next to where we put the pilot treatment facility, and we were able to just discharge it to the sewer system.
Ida, for a full-scale project, would it still go into the sewer system, or would you try to bring it to the brine line?
It would be ideal if we could bring it to the brine line, but it depends on you know, the future plan. But for now, we are assuming that it's just gonna go to the wastewater collection system, because it doesn't come close. It involves a lot of new pipeline to connect it to the SMP line.
Great, thank you. The questions keep on rolling in. This is great. The next question is from Megan Plumley. Hi, Megan. And her question is, what led you to choose the pilot CCRO? For example, there are other cases of water agencies using CCR. Are there other cases of water agencies using closed circuit RO for brackish groundwater?
It's a good question. I'll take that and answer it as best as I can, Megan. It's a good question. I'm not as familiar with other full-scale municipal projects using CCRO as the primary RO for brackish groundwater. I believe there are others, at least outside of the state, but I'm not familiar with others that are operational right now inside the state. So that was one of the reasons why we were interested in piloting it. Also, it's had other similar good performance in pilot testing for other applications, such as for brine concentration. Brine concentration is like 3rd or 4th stage on other systems.
Great, thank you, Steve. Next question is from David Ailes, and I think this is for you, Steve. What % of the permeate flow reduction was used as your CIP or clean in place set point?
It's a good question. I don't remember the exact numbers. It varied depending on the metric that was used. We looked at 3 different matrices. So we look at normalized differential pressure, normalized permeate flow or permeate flux, and normalized salt passage. Each of them had a critical threshold that was used. So depending on which one met that or exceeded that threshold first was what triggered the CIP.
Great, thank you. And Steve, I think this is also for you. This is from Richard Breckenridge. Was there bench studies of pH control for calcium carbonate and silica, as low pH is good for hardness scale, but not for silica?
I'm sorry, I don't know if I understood. Was the question, was there?
So I think it's were you able to do bench studies of the pH control for calcium carbonate and also for silica? And Richard is pointing out that low pH is good for hardness and scale, but maybe not for silica, I think is what the question's getting at.
Yeah, exactly. The short answer is no. We did not do separate bench testing or bench studies on that. But yes, essentially that was one of the results of the pilot testing, that we found that with the conventional RO, that the pre-pH adjustment was counterproductive to the recovery and overall performance as a result of the silica scale being the limiting scalant. During the desktop studies that were done previously based on historical data, calcium carbonate was identified as a limiting scalant, which is why we initially had sulfuric acid in the treatment train.
Fantastic. Well, we're doing good on time. I actually have a question for you, Steve. Earlier in the presentation, you said that the CCRO uses existing RO equipment, regular membranes, regular cartridges. Can water agencies, if they're looking to increase recovery from their existing plants, can you retrofit CCRO into an existing facility?
I think I would certainly defer to DeSalotech on the details of that. So DeSalotech was the supplier, DuPont DeSalotech. My understanding is yes, that it can be to the extent of those retrofit and requirements. It sure depends on case by case.
Okay. We have time for more questions. Ida, I've got one for you. What's next? What's the next step for the pilot study or for this project? And yeah, someone had a question. What's the timeline for the full-scale project? And I think this is a question for Ida.
Sorry, I was muted. I was talking, but I was muted. Yeah, it's a good question. We are currently, as I mentioned, we started a 6-month pumping test back in August 2020 to confirm the sustainable yield of the well, because this well hasn't been used for a long time. We just wanted to make sure that it can meet, our flow requirements, the 770 GPM. And we did a extended pumping test, and it's terminated. And now Steve and Kennedy Jenks consultant, with the help of Hopkins consultant, they are monitoring the recovery rate to confirm the sustainable. It's not gonna be as much as we predicted, like 770. For sure, it's gonna be less than that. The results so far shown that it's gonna be less than that. And after we confirm that number, and also depending on how much grant will be available, next step would be to wrap up, to finalize the PDR, and then start full design scale. Yeah, hopefully. Yeah, but it's mostly depending on that, confirm the number of, the sustainable yield of the well. After that, we can pursue with the full scale design, hopefully.
Great. Do we have any other questions from the audience? It doesn't look like we have any open questions. Well, that sounds like a great way to end this particular webinar with the schedule for the next steps. I want to thank you both, Ida and Steve, for this excellent presentation. I know the results for this study will help other water agencies, and that's the goal of this program. I think we're done with the questions for today. But before we close, I want to thank our member agency partners with Calleguas. That includes Dan Drugan and Jennifer Lancaster, who helped really keep this study moving during COVID, and were essential partners in this process. I also want to recognize the Metropolitan FSA team. That includes Hannah Ake, Don Bentley, Matt Hacker, Ariba Saeed, who was the study manager on Metropolitan side for this study, and also Teresa Gonzalez and Stephanie Franco. Without their work and hard work and efforts here, the FSA program and this webinar would not be possible. Finally, I want to thank everyone who tuned in to today's webinar. We know that you got hundreds of webinars to choose from in any given week, and we're ecstatic that you joined us. But this is part of a series. The next webinar in this series will be on stormwater. and it's going to be hosted by the Southern California Water Coalition on August 10th at 10 p.m. Again, we're going to be posting this recording, the final study, the slide deck on our website in the near future, and we'll send out emails to let you know when we do that. And without, oh wait, do we have one more question? No, okay, just a comment. So please take care. Again, thank you for the, Ida and Steve, but everyone else, take care. Take care of yourselves and your families. Have a great rest of your day, and we'll see you at the next webinar. Thank you very much. Thank you.